It's a pleasure to be back at KITP. I've given many talks in this room. There are also many people in the audience. I see many collaborators here. It's great. Thank the organizers for putting together this fantastic conference. Very exciting. And this is the title. I'll explain the title, what I really mean by ordering here. There are about 2 or 3 different meanings of the ordering at the beginning. And these are my collaborators. There's a paper to appear. I think that the 0 is not too optimistic, but we'll see. So some of the people here, as you can see, are card-carrying condensed matter physicists. Some of them have background in math, and some are in field theory. And this is typical for this conference, and for this topic in general, that we have a nice collaboration of people from different sides, and that is really great. And I think a lot of science should learn from this collaboration between different disciplines. But it also raises a challenge that in the overlap regions here, we need to have some transition functions. And these transition functions should better satisfy some co-cycle condition and be consistent here. And I will later in the talk at least allude to, and if there are questions, I'll be happy to say more, where actually the transition functions are inconsistent. I alluded to that a little bit in the previous talk. So as for this talk, since we have this mixed audience here, there will be some slides that will be rather elementary, kind of to make sure that everybody is on the same page, and targets different communities. And it's embarrassing for me because I know that there are people in the audience who know more than I on some of these topics I will review. Sorry? Who said that? I'll kick you out. Raise your hands before you talk. But what really helped me was that Clay gave this morning a beautiful introduction to some of these materials. So before we start, maybe we should put kind of what are we talking about. So we're talking about quantum field theory in some background metric coupled to a background U1 gauge field. So the metric is not fluctuating, at least not in this talk, and the U1 is not fluctuating. This is just a background field. And we should distinguish 3 kinds of theories. First, if microscopically we have bosons, that's the easiest case. We just have what we could call a bosonic theory. This is almost a tautology. Slightly more interesting and more complicated is we have fermions. If we have fermions, we need to have a spin structure, and the answers could depend on the choice of spin structure. And we can define the theory only on the spin manifold. And slightly more interesting theory is the theory we can refer to as electronic. It is the one with most interest in condensed matter physics. It does include fermions, but it does not need to be on a spin manifold. Instead, it needs a spin C structure. This thing arises when we have bosons with even charge and fermions with odd charge. And what happens here is that we use the background gauge field A in order to fix any mistake, quote-unquote mistake, in the fact that spin structure does not exist. In condensed matter language, this thing occurs when we study many electrons interacting with each other. Strong-Coulomb force could be very complicated. This could be a guiding principle that we should follow. If neutrons are involved in the process, this guiding principle is no longer there, and we have fewer constraints. So it's to be oriented, the fermionic theories is the largest class. Some of them are also bosonic. It's a subset of them that do not depend on the choice of spin structure and can be defined on other backgrounds. And others are spin C. And we'll see examples of that later. So this is background for some set of people, background for other set of people. It's a classical Hall effect. We put a magnetic field. We put voltage in one direction. We get current in the opposite direction. And it's characterized by a response theory, which looks like that. There are also many other terms that I exclude, like various gravitational terms and other couplings to the background gauge fields, but for the purpose of this talk, let's just focus on this coupling. So this is a classical theory, has equations of motion, and the equations of motion tell us, we obtain by taking derivative with respect to A, so the current is perpendicular to the electric field, and the charge density is proportional to the magnetic field. This was completely understood in the 19th century, so this is really ancient stuff. Moving to the 20th century, we move to the quantum theory, and for simplicity, I'll set h bar to 1. Now the response theory is in the exponent, And then we have to ask ourselves, is this response theory well defined? And the answer is yes, provided two conditions are satisfied. Either for bosonic systems, sigma h has to be an even integer, and for fermions or electrons, sigma h has to be an integer. So this is the coefficient here. There's no such issue in the classical theory because this quantization has an h bar buried in it, which we set to 1. And this is just to make sure that this response theory is well defined. And then this thing in the exponent is the action of a 2 plus 1 dimensional field theory. And in physics terms, this means that the system can be trivially gapped, and even then, but even then it could be non-trivial as there could be edge modes. This is the integer quantum Hall effect. Okay, so to make it a little bit more interesting, for the purpose of this talk, we'll be mostly interested in the fractional sigma h. That corresponds to the fractional Hall effect. And then the response theory is not well defined. How did we get an ill-defined response theory? By taking a system that does exist, and we measured A, and we found this response theory. The answer is that the effect of this means that the low-energy theory cannot be trivially gapped. And even if the system is gapped, but not trivially gapped, it is described then by a non-trivial TQFT. And we got this response theory by incorrectly integrating out modes in the TQFT. That's why we got an ill-defined object. And for the rest of the talk, we'll just get mileage out of the fact that this object is ill-defined. And it's ill-defined, but we can always add a sigma h, which is an integer or even integer, depending on the theory. And condensed matter physicists call it stacking an integer quantum Hall system to it. And for the purpose of this talk, I'm going to ignore that. So I'm going to work modulo adding this integer. So we are interested in this fraction, and such a fraction in the Chern-Simons theory is a useful diagnostic or characteristic of non-trivial quantum field theory. For example, it has been used in the study of gap in dualities between supersymmetric theories in this paper. And our goal here is, in this talk, I'm going to limit myself to gapped phases, and then we have a TQFT. And the question we are going to address, this is where the talk really begins, given such sigma h, which is P over Q, P and Q are relatively prime, what can we say about the TQFT? So it's a very concrete problem. We measured the whole conductivity. We know P, we know Q. These are two integers. We divided as much as we can so that we get two integers. And what can we tell about the TQFT? And here we have two perspectives, the condensed matter perspective and the high energy perspective. And we can tell the story separately in each column, but I wanted to put them one next to the other so that we can see the comparison. So the field theorists would say the Chern-Simons theory, or the response theory, is not well defined, reflecting an imprecise integration out of the TQFT modes. That's why we got an ill-defined answer. The condensed matter physicists, going back several decades, I'll soon give references, use what they call flux threading. They put the system on an annulus, and they thread flux through the interior of the annulus, and they gradually change A sub x, x running around the annulus, from 0 to 2 pi over L. That doesn't change the holonomy. So at the beginning of the process and the end of the process, we have the same background gauge fields, but since the response theory is not well defined, we don't get the same answer. Why did it happen? It happened because the TQFT has several states, and if we start with one state, at the end of the process we ended up with another state which would not have integrated out these distinct states. And they differ by taking a particle referred to as a vison from one side of the annulus to the other. And you see the references go back to the 80s and tons of references after that. And by examining it more carefully, we know that the charge of the vison is P over Q, and its topological spin is P over 2Q. And since we have a finite number of visons, we have a TQFT, it means that if we raise it to some power, at some point it stops. We go back, we find a trivial case. So this is how we define the integer s. The integer s is defined as the power of the vison, which gives us 1. It must be a multiple of Q. Going back to the field theory column, we say, this thing is ill-defined. How did we get it? The only way to get it is that the bulk theory, the boundary theory, the TQFT that we discussed has a ZS one-form symmetry with anomaly R, and P and Q that appear in the Hall conductor are related to this S and R in the following way. And the generator of this ZS symmetry determines the charge of all the anyons via braiding, so that's the Wison from this side. So you see the relation between the two. Being a field theorist, I'm going to continue with this column and do it now in more detail. So this is not well defined, so how are we going to define it? Here is a way to define it. We add a bulk, 4-dimensional space-time bulk, and instead of writing this Chern-Simons term that is ill-defined, I'm writing a 4-dimensional theory, dA. Now at least I know what I'm talking about because this thing is globally well defined at every point in space-time, and then we can integrate it. The price we pay is it depends on more data. So this thing is what the definition of a response theory I would take, and it depends on more data. And now I'm going to ask, how can the TQFT lead to such a term? So this is the only way this could happen. The TQFT has a ZS one-form symmetry, S soon to be determined, and we couple it to background gauge field B. This is a discrete gauge field. And then the 't Hooft anomaly in ZS is labeled by an integer R, and this is the anomaly theory. So anything above this point, forget where it came from. This is a separate, well-defined statement that given a one-form symmetry ZS with anomaly R, we can turn on background field B, and the anomaly is given by this expression. And if you don't know what Pontryagin square is, think of it as B square. That's not quite right, but it's mostly right. Okay, how am I going to use that? I'm going to use that by coupling the background gauge field A, the electromagnetic field. I'm coupling it to the TQFT through its coupling to B. So roughly, B will be dA over 2 pi, and the roughly, this is a footnote, is because B is a discrete field rather than a differential form. This is a differential form, and that's not exactly a square. But if we ignore that, and we just substitute B equals dA, this thing is written in this form, and then we can write it in terms of the boundary and find our ill-defined response theory. So the upshot of all that is that the ill-defined response theory reflects a one-form symmetry with an anomaly, and the anomaly theory of the one-form symmetry becomes the response theory of the background gauge field A. So now we are going to analyze the symmetry lines of that one-form symmetry, because we would like to get, what can we say about the TQFTs? Okay, so we said it has some symmetry lines and some anomaly. We'd like to get more beef out of it. We'd like to get more information. So we should study these symmetry lines. And first, that's what we did in this paper long ago, we ignore the U1. Imagine there is no U1 in this story. So the one-form symmetry is generated by V, the Wison V. It has anomaly R, and it has S symmetry lines. So this is the set. It has 1, V, V square, and it stops at V to the S. And furthermore, just from the symmetry, you can learn that the topological spins of the lines are given by this well-defined formula. So just by knowing the symmetry, ZS, and the anomaly, we know quite a lot about the symmetry lines. Now, V to the S should be a transparent line, and in particular, its spin is restricted by that. So if the theory is fermionic, the spin should be 0 mod a half, and therefore R and S should be arbitrary integers, and R is identified with R plus S. If, on the other hand, the bosonic theory, if on the other hand we discuss a bosonic theory, which could happen if we have a system of bosons interacting in some way, H is further restricted to be 0 mod 1, and then R times S has to be even, and R is identified with R plus 2S. This 2 here is the same 2 that appeared earlier when I talked about the integer Hall effect for bosons. In this case, we did not discuss the U1, and therefore there is no spin C. Now let's turn on the U1 and see what additional information we get about the one-form symmetry. So the formula for H is the same, and the electric charges, or the Q1 charges, are given by the ZS charges of every Wison, of every anyon. And for the fermionic theories, this is unchanged. R and S are integers, and R is identified with R plus S. For bosonic theories, it's essentially as before, so we get the same answer as before. So it's the same as the fermionic. We have one more restriction on H, and therefore this has to be even, and we have a factor of 2 in the identification. More interesting for us are the spin C theories, because now it's the same as the fermionic theories, but we have another restriction. All this algebra on the slides, don't try to follow it in real time, because it might be challenging, but this is something you can really do in your head. There isn't a single calculation here that you need a pen, let alone Mathematica. It's really completely straightforward. So for spin C, we have another condition, and this condition translates to this restriction, R S plus 1, and R is identified with R plus S. And connecting back to physics, the fermionic ones are the easiest to think about, but the spin C is what's relevant for electrons, say, in a magnetic field. So the simplest case to study is when L equals 1. So when L equals 1, S and R, so this is kind of the minimal thing we could do. We had P and Q coming from the response theory, and we just set S equals Q and R equals P. In this case, the symmetry lines realize the ZQ symmetry faithfully. And this has already been mentioned by Clay, I guess, that in this case the theory factorizes. The theory factorizes into the symmetry line times the rest. And the rest is invariant under the discrete symmetry, and therefore it's also neutral under the U1 symmetry. And of course, you could have told me from the beginning, if you found any TQFT that leads to some sigma H, some P and Q, I can produce another one by tensoring a totally decoupled TQFT. Of course, it's not going to change anything. So here is an example, and of course there was going to be an ambiguity in tensoring this thing, but since I'm after the minimal one, I'm going to ignore that ambiguity and focus only on the minimal one. So that part of the theory is trivial from our perspective, and we are going to ignore it. For other perspectives, it might not be trivial, but from our perspective, it is trivial. So we end up with a minimal theory, this VQP. This has Q lines with anomaly P, and that's the answer. So given P and Q, in this case, L equals 1, I know what the answer is. The answer has to be that. For L not equal to 1, these symmetry lines are not a complete theory. More technically, they form a pre-modular category, but less technically, the symmetry lines do not realize the symmetry group faithfully, and therefore there must be more lines in the TQFT. So imagine we have a theory with L not equal to 1. So L is not equal to 1, and we'd like to reduce L because we would like to find the minimal theory that could be there. So how are we going to reduce L? The procedure is gauging. We have a one-form symmetry. We would like to gauge a subgroup. We would like to gauge a ZL subgroup of the symmetry. So we try to gauge it, and the first thing we notice is that the ZL subgroup doesn't have an 't Hooft anomaly with itself, and therefore there is no obstruction to gauging it. However, very interestingly, this ZL one-form symmetry is an anomaly with a metric, which we will soon see, with a spin structure actually, which we will soon see. This will give us information. So we are trying to gauge it, and in some circles, this procedure is known as condensation. I'll put a fine print in a smaller font that I've had issues with this terminology, which I shared with many of you guys over the last several decades. I think it started in 2002, 2004 when this thing was introduced, and this is fundamentally misleading. If I'm asked about that, I'll say later why it is misleading. I already complained about this earlier today. When I said it, I sound like a broken record, because I do sound like a broken record. But for the purpose of this talk, I'm going to call it gauging, and therefore I don't have to address this thing. So let's start with fermionic theories. Now there's no restriction, there's no anomaly, and therefore we can gauge the ZL. And if we gauge it, we find a smaller theory with L equals 1. And then we can just go back to the previous slide. L is 1. The theory factorizes. I throw away the neutral part. And what I'm left with is this minimal theory. This is very satisfying. Knowing V and Q, if I gauge whatever I'm allowed to gauge, and I throw away whatever is decoupled, I always end up with the same answer. Let's move to the bosonic theories. Now we have a restriction that R has to be even. But that would mean that if we try to gauge, PQ should also be even, because that would be the result of the gauging. This puts a restriction on L, which can be interpreted as an anomaly. We have an anomaly between the one-form symmetry and the existence of and the choice of spin structure, or the independence of the spin structure. So if PQ is also even, there is no problem, there's no anomaly, I can gauge whatever I want, and then I end up again with a minimal theory, just as before. If PQ is odd, I can only gauge half of it, gauge only ZL over 2, and we end up with a smaller set of symmetry, smaller symmetry, but not the minimal one, because the two things in the superscript here are not relatively prime. So this TQFT does not factorize. Here is an example that people have studied. Clay gave a description. He mentioned the paper by Zhang, Vishwanath, and Wen, which has a long catalog of examples. In bosonic theories with sigma h equals 1, this corresponds to one field Landau level. So sigma h is 1, so p is 1, and q is 1. And therefore, the smallest symmetry is V22, because it's 2p and 2q. And that by itself is not a complete TQFT, but it can be embedded in some TQFT, for example, spin n level 1. So the difference is between PQ being odd and PQ being even. So that's bosonic theories. We've done fermionic theory, we can gauge all the way to the end. Bosonic theories, depending on PQ being odd or even, we can gauge all the way to the end or only half the way. Spin C theories are the most interesting ones, because there we had this selection rule. The theory makes sense only when R s plus 1 is even, and that translates into some conditions on P and Q. So if Q is odd, we can gauge the entire ZL and end up with a minimal theory as before. If Q is even, we can gauge only ZL over 2, and we end up with this more complicated theory. And the theory does not factorize. So I don't expect people here to follow all the cases. This is even, this is odd, spin C, bosonic. It's not easy to follow. But if you go carefully through it, these are things that you can count on your fingers. It's really easy and straightforward. And this is kind of a complete classification of all cases. Let me give an example. Sigma h is a half, p is 1, and q is 2. And therefore, doesn't satisfy this requirement, or if you wish, q is even. And therefore, this is the symmetry. There's a Z4 one-form symmetry with anomaly 2, and it can be embedded, say, in U1 level 8 or more read. So this is a result that many people here know. For a fractional Hall effect, as we know, for fermions, it's a spin C. Odd denominators and even denominators are completely different. And here, we got it just from understanding the structure of the TQFT. So this is the part I wanted to go through in detail, but I want to give you a glimpse of other things in the paper. So additional topics, and I'll go quickly through them. The first, where did this one-form symmetry come from? After all, there was no one-form symmetry in the formulation of the problem. So one answer is that the one-form symmetry is an emergent symmetry. It wasn't there to begin with, but luckily we ended with it in the end, and given the value of sigma h, given the values of p and q, we learned something about this TQFT that we found. But there is a more satisfactory answer. Imagine we study this system as a system of electrons interacting with each other. It's quite complicated, in a constant magnetic field. If the magnetic field is constant, the UV theory has translation symmetry. But because of the magnetic symmetry, because of the magnetic background magnetic field, the magnetic symmetry becomes the magnetic translation, which is actually, for finite volume, is a discrete symmetry with an anomaly. In that case, for electrons in a constant magnetic field, the IR one-form symmetry that I talked about really started its life as translation of the UV system. So the UV translation of this system is transmuted to the one-form symmetry I talked about here. And Sahan is going to talk tomorrow about symmetry transmutation in general, how symmetries of one kind in the UV can transmute into symmetries of a different kind in the IR. So this is an example of it, where in the UV we had translations. The system could be very complicated. We have electrons, but the system is exactly translation invariant. And there was some interaction. We found a gapped phase with some TQFT. The TQFT has a one-form symmetry. This one-form symmetry reflects the exact translation of the UV system. But since the IR system is gapped, this symmetry is robust. So now we can go back to the UV and add some impurities. Maybe the magnetic field is not exactly constant. Here we don't have a magnetic field. We can get the same response without it. Our entire reasoning is still correct. So this is very common. Sometimes the one-form symmetry in the IR, you can trace it back to something in the UV, and sometimes it's a new, but then you can deform the system and break the symmetry. Another topic we discuss in the paper is extending it to bilayer systems. So now it's a little bit more complicated. You have more gauge fields, and there are more restrictions, but the same machinery can still apply. And we also give a more detailed picture of how this ZS symmetry generated by the Vizon can be embedded in a TQFT that has a much larger one-form symmetry. It should still be a subgroup of it, but it can be embedded in many different ways in an interesting way. And we also have lots of new results about spin and spin C TQFT. This goes a little bit outside my comfort zone, and there are people in the audience who know more about it, and I'll be happy to hear from them differently. There isn't much discussion in the literature, as far as I can tell. In the category literature, most of the work is about bosonic systems. There is a lot of work still on spin systems or fermionic systems. I have not found much about spin C systems, because that gives some more relations. So we did some of that ourselves. And there are a few other topics that we can discuss. So in conclusion, it's really fitting for this conference that the organizing principle of the quantum pole system is a one-form symmetry. So the thing that really runs the show, the thing that tells us how to organize things, is the one-form symmetry and its anomaly, and that's the organizing principle. And for every value of P and Q, there's a natural minimal topological field theory. So these are the different meanings of order here. We found an order that some of them are more minimal than others. We also put some order in, I think Clay said this morning that there's zillion, where is Clay? He said that there are zillions of papers addressing various examples of, I think that's the word you use, zillions of papers addressing various TQFTs. It's really not fun to go with this understanding through this paper and say, oh, that's just obvious because of this fact, this is obvious because of that fact. So that's kind of put a lot of order in that system. And this is the result for when the dust settles. For bosonic system, when PQ is even, which means that either P or Q are even, we cannot have both of them being even. We have a minimal abelian TQFT with Q anyons. That's the answer. So this is the minimal theory. And for odd Q, this is the minimal symmetry lines. And the full system, this should be embedded in a bigger theory. It's a little bit more complicated. And more interesting, perhaps, are the spin C theories. And again, for odd denominators, for odd Q, we end up with this minimal theory, QP. And with Q is even, it's a little bit more interesting. The minimal symmetry is V2Q, 2P. And this has to be embedded in another system, for example, in Moore-Reed or U1 level 8. Surprisingly, most and perhaps even all the known examples among the zillions that Claire referred to, we have not checked all zillions of them, but all the examples that we looked at in the literature are the minimal ones. So that's what people found, probably because you don't go to a more complicated construction if you can have a simpler one. But that means that the zillions of papers that Clay mentioned are summarized on this slide, actually half a slide. I think I'm finishing on time, so I'll thank you here.
In the case that you mentioned where you can't get down to purely a minimal TQFT, can you give some further refinement of how it can be embedded? And what would that look like?
Yeah. So the answer is yes, and there's still a notion of minimality, because you could say, what do you mean by minimal? So you could say it has the smallest number of anyons. or it has the smallest quantum dimension. And if you adopt any of these, there's a finite number of possibilities, because, yeah, for obvious reasons. In many of these cases, it's very easy to guess how you can, so once you know the symmetry lines, you can ask, what can I add in order to make it a complete TQFT? And if you just look at it on a case-by-case basis, I do not know a general algorithm, but first of all, you need to add lines that transform non-trivially under the one-form symmetry, because the V does not realize the symmetry faithfully. You know that very well. So, so you add some lines to do that, and then it's kind of, you just look at it and you immediately know. So U1 level 8 is an example, Moore-Reed is another example, and among the zillions of papers that you mentioned, there are quarter zillions, which are other examples.
Hi, Nati. Just two quick questions. One is, you mentioned at the very beginning a background metric, but I don't think you talk about the background metric at all.
You're right. Actually, that's spin structure.
Secondly, how about the non-abelian case?
You're completely right. I shouldn't have said metric, I should have said topology, and then I would have been covered. The thing is that sometimes it's spin structure, sometimes it's spin C structure, and depending on which model we're talking about. So I was slightly imprecise. As I said, on every topic I talked about, there's somebody in the audience who knows much more than I do, and that proves my point. The non-abelian case is very interesting, but one lesson from this is that the symmetry lines that I know have to be there are all abelian. Abelian, so first of all, invertible and abelian. Now, in the two cases that are slightly more subtle, that I mentioned in this and that, odd PQ here and even Q here, where you need to embed it, then typically the system is non-abelian, but it doesn't have to be non-abelian. But the thing that really drives the show is this V, the abelian anyons generated by the Vizon. They really drive the show. Everything else is there, either completely neutral, and we can forget about it, or it is there only to make the theory modular. It has no other purpose in life. But what gives the sigma H is these guys. They give sigma H. And the rest is there kind of to make the whole thing hang together.
What happens if you also add the chiral central charge in the game, apart from this? Because it's also a response that you can measure.
We haven't done that, but we know what needs to be done. What we need to do is to add the gravitational Chern-Simons term with a known coefficient, and that would give us further restrictions on the theory. And it's completely straightforward to do that. But this is already a huge simplification. You take zillions of papers, as he said, and you summarize them in half a page.
Thanks for the talk. You mentioned the minimal TQFT, and there's like many different definitions, like number of anyons or quantum dimension. Given any reasonable definition, is the minimal TQFT unique? Given
okay, so in the easy cases, which mean PQ even here and Q odd here, this is the minimal theory. It's unique. In the other cases, the symmetry lines are unique. And for a given, if your criterion is minimal anyon numbers or minimal quantum dimensions, there's a small set of possibilities. Because you can always embed it in something bigger. So what did we do? We said, if we can gauge whatever we can gauge, some people would say if you condense whatever you would like to condense, or whatever you could condense, so you go down. If you have done that, and then you throw away whatever is neutral and decoupled, if you're left with a TQFT, you declare success. And that's what this thing is.
Could you please elaborate on the issue you mentioned with the condensation terminology?
Oh. I'll be happy to do that, but I would like to hear his question. And if I forget, please come back and ask. Because that would be easier. And I see Lucas is getting anxious.
Yeah, thank you. So you mentioned the origin of this one-form symmetry as UV translation, but I suppose that is continuous translation symmetry, right?
Yeah,
Then my question,
not quite. It's continuous translation becomes a discrete translation in a magnet.
Okay, yeah. So my question is, if we start from lattice system with discrete lattice translation symmetry, I think some time ago we derived some constraint coming from this lattice translation on whole conductance. So I'm wondering if you can.
Okay, I'm not.
apply.
Please send me the link to this
yeah.
work. I'm not aware of that. The argument based on if you just have just continuous translation, which is the biggest symmetry, the argument is extremely straightforward. If you have a continuous space, then and you have k fluxes through the torus, there's a zk times zk one-form symmetry, and it has an anomaly, and there's a mixed anomaly between the two zk's. But depending on the filling fraction, some of the anomalies is not there. So what you really have to realize in the IR is that part of it which does have the anomaly. The rest you don't have to realize in the IR. So the freedom in L is in realizing too much. But the rest, so what you're left with is the K that you have there. So it's K it depends on the filling fraction. So it's the number of electrons divided by K. That's the anomaly of the translations in the UV. That becomes sigma H. We know that this becomes sigma H in the IR, but from this perspective, this is the anomaly in the one-fold symmetry. And please send me a link to your paper.
Thank you. Yeah.
Yeah, I have a question.
Okay, Mason.
Either one.
And then, no, don't go away.
Well, I just wanted to ask more about the translation. I mean, if I just have U1 symmetry, then there's some U1 symmetry fractionalization. It's determined by the Vizon, and then you get everything. So why did you need to even mention translations?
Because we are completely right, but somebody could ask, where did this come from? So let me give you an example that you know very well. Imagine I'm studying Z2 gauge theory. I don't care where it came from. It has a one-form symmetry, etc. But people say it's wonderful to have the toric code, which has a much larger symmetry, and we can analyze everything in the UV with a larger symmetry and understand where the one-form symmetry of the IR theory came from. And this is considered an advance, and it is an advance. And then, since the system is really gapped, you can deform the UV, break the symmetries in the UV completely, but many of the results in the IR are the same. So the same thing is true here. You can say, okay, you got a TQFT, the TQFT has a one-form symmetry, I can study that. That's great, but you can ask, where did this come from? And I'm telling you that in some cases, I know exactly where it comes from because I have a microscopic system which has a symmetry with an anomaly, and it has to match, and it's matched through this symmetry transmutation that Sahan will talk about tomorrow. Since I'm running out of time, I'll answer this question. Gauging is a map between two different theories. Example, you take free electrons and you gauge the U1. What you end up with is QED. You do not say that there's condensation between them, right? This is a map between two theories. You can embed it in another theory with a scalar field that would Higgs the gauge field, and then the Higgs transition can be referred to as a condensation. The phenomenon that we talk about here is a little bit more clear that these are different theories, because the symmetry is a little bit more subtle, because A, the symmetry is a one-form symmetry rather than a zero-form symmetry, and second, the symmetry is discrete. This is as it was until early 2000. And then some people decided to interpret that as condensation. And I remember many people said this gauging of one-form symmetry is condensation, and Greg and I in particular were really screaming and kicking that, no, it's not, it's different physics. This is gauging, it's not condensation. And then I learned from some people, I think it's Pochen and Otat and maybe others, and also Mason and Monk showed me something similar. I shared this grievance with them. And was it 10 years ago, give or take? And they showed that in some cases you can actually find a UV system that performs this transition. The UV system messes up the one-form symmetry. That's one of the hallmarks of the UV system. But it is what it is. And it is convenient if you want to find a system in the UV that has a phase transition between these two phases. So in the paper we're writing now, we show examples where this is actually not true. And you actually cannot embed it in this theory, which it just restores the sanity. It's not something that, oh, surprise, it doesn't work. It shouldn't have worked from the beginning because conceptually these are different things. This was not a complete answer, but I think they're going to kick me out of here soon.
Thank you.
For another question. I was wondering if the results here can be, if you could comment about the relation of this to the width group somehow.
To the what?
The width group.
Oh, I can very quickly. No. No, not that there is no relation. I cannot comment on this.
Again,